Hello everyone, today we're talking about model predictive control of a Segway PT scooter while turning. And first, we want to give our special thanks to Professor Borelli for his help and support. The team members include Dee, Zane, Zihe, and Dante. Segway PT is a two-wheel self-balancing scooter. This scooter was invented by Dean Kamen and was first introduced in 2001. As more customers starting to adapt to this new way of transportation, the concerns on safety of Segway scooter arise. It is more likely for customers to lose balance while turning the Segway. Victims could suffer from severe facial and brain damage if losing balance and falling off the scooter. Thus, this report investigates using MPC to stabilize the Segway while turning. The dynamic model of a Segway turning circle can be simplified into a Furuta pendulum, or a rotational inverted pendulum. The Furuta pendulum was first introduced by Furuta at the Tokyo Institute of Technology. The Segway model can be derived from this model. This turning radius is corresponding to the driven arm 1 in Furuta model, which can be freely rotate about a center point z-axis in the horizontal plane. The control arm is corresponding to the pendulum arm 2 in Furuta model, which can freely rotate in the vertical plane perpendicular to the horizontal plane.
Hello, I'm Zane. I'm going to talk about the dynamic model of the Segway. First, I want to introduce the meanings of the variables. L1 is the turning radius. L2 is the total height of the human and the Segway. Theta 1 is the angle of the Segway to the origin point. Omega 1 is the angular velocity of the Segway to the origin point. Theta 2 is the angle of the body to the perpendicular position. Omega 2 is the angular velocity of theta 2. We used the Lagrange method to calculate the dynamic model. First, we pick a small part of the Segway. The part is named dl. We calculate the kinetic energy of this small part dt. By the integral of dt, we get the kinetic energy of the Segway. Then we calculate the potential energy V, and by Lagrange method, L equals to T minus V. Because there is no force on theta 2, we can calculate the theta 2 the second. And because there is an equilibrium point at theta 2 equals to 0 and omega 2 equals to 0, we can use the Taylor expansion to linearize the system. So we get a linear model of the system. It has 4 output variables and 1 input variable. In addition, when there is friction, the matrix only have a small difference in the last element, but it is still linear.
Hello, this is Zihe. The first part of the research is to stabilize the model with most possible parameters in constrained finite time optimal control. The simulation was meant to observing the possibility of recovering from a sudden imbalance within a certain amount of time while making a turn. Thus, the initial constraint was set to be initial angle theta 1 equal to 0 radius, theta 2 equal to pi over 6, and the initial angular speed omega 1 equal to 0.7 radius per second, and omega 2 equal to 0 radius per second. And also we set the time horizon to 10 seconds and the sampling time ts equal to 0.01 seconds. Since the target is to recover to a stable standing state, the terminal constraints was set to be theta 1 equal to 0, and we didn't put any constraint on theta 2, and we also set omega 1, omega 2 equal to 0 radius per second. The inequality constraints involves the limits of angular speed, angular acceleration, control arm maximum sway range, and also a spatial constraint saying that for the safety of not hitting things behind the Segway should not go back too much. And also the cost function we used for MPC is listed below. From the result of our optimization, we can see the omic 1, omic 2, and date 2 converge to 0, as well as the alpha 1 converge to 0, which shows the stability of our system. And finally, the date 1 converge to a very small value, which is also acceptable for us.
Okay, so this is Dante speaking. So now we know that CFTOC stabilization is kind of successful, and after several iterations, we are sure that for most of the cases, the CFTOC can be stabilized within 1 second, and that's why we set the prediction horizon to a total of 1 second. And since we give our sample time to 0.05 second, we have the number n, which is the prediction horizon, to be 20, and also for the simulation horizon, we want to see a bigger picture, so we set it to a range of 4 seconds, which corresponding to 80 for the m. And also for the initial condition, as previously speaking, we want an initial speed for omega 1, which is like 5 kilometers per hour divided by something. And also we want an inclination angle. After a lot of tests, we find that for our cases, we have a forward inclination of 45 degree and to the range of negative 30 degree for the inclination angle. The reason why we do not do more than 45 degree, even though we know it is going to be successful, is that we believe that after 45 degree, the inclination is too extreme, and this case is very rarely happening, and is like too extreme it's not so meaningful to be explored. And also for the negative 30 degree, we find that for any angle larger than the negative 30, I mean smaller than negative 30, the system will be very likely to be unstable, and thus for a safety issue, we want to keep it to 30 degree. And also we investigated the effect of turning radius. At first, we expected that the larger the turning radius is, the faster and easier the control should be. So we tested 4 value for the L1, which is turning radius, 1, 2, 5, and 20 meters. For our result, very surprisingly, it is very not clear that the stabilization speed has any relationship with the effect of turning radius. I mean, actually, we can say it's slightly that the larger the turning radius, the slower the control is, but it's gonna be proved later. In the next time. But obviously, we find that the larger the turning radius is, the easier and less overshoot the system would be. And most obviously, if you see the L1 equals 20 curve, there is basically no overshoot. I mean, the overshoot after 0. So it is say that the system goes very smoothly to the end. So in conclusion, the MPC is very successful, and we investigate a range of positive 45 degree to a negative 30 degree, and that is very desirable. And also we investigate the effect of the turning radius, which indicates that even if for special cases, if someone is driving too fast to turn, or if the inclination angle is too large, if we increase the turning radius, it still can be balanced, possibly. So that's why people always want a larger turning radius. And that's it. Okay, so thanks for watching. That's it.